In a single switch NDI deployment, bandwidth is relatively easy to manage. All devices communicate within the same switching fabric and traffic remains internal. But as soon as the infrastructure grows and multiple switches are connected, inter-switch bandwidth becomes a critical factor. When NDI streams need to travel across switches, especially from sources connected on one switch to receivers on another, the uplinks between switches carry that traffic. Now, if they're not properly dimensioned, these uplinks can quickly become saturated, leading to visible issues such as frame drops, stuttering video, or increased latency. So to avoid these problems, it's essential to approach multi-switch network design with the following strategies. First of all, assess the bandwidth requirements accurately. Each NDI stream has a predictable bandwidth footprint. Full HD 1920 by 1080 at 60p, for example, is 125 megabits per second. 4K is 250 to 300 megabits per second, depending on the frame rate and format. So, if we multiply by the number of simultaneous streams traversing a link to understand the worst case scenario link upload, we can then figure out exactly what we need for these uplinks. We also need to use high capacity uplinks and link aggregation, or LACP, link aggregation control protocol. Even a handful of HD NDI streams can saturate if two switches are connected with a single 1 gigabit Ethernet link. Whenever possible, we need to use 10 gigabit Ethernet or 25 gigabit Ethernet or higher capacity uplinks, such as 40 or even 100 gigabit Ethernet, which are becoming more and more affordable. Implementing link aggregation control protocol to bond multiple physical links further increases available bandwidth and adds redundancy in the case of failure. We can implement VLANs for logical separation. While VLANs don't directly reduce bandwidth usage, they do help to isolate traffic types, keeping NDI streams separate from management, control, or internet-bound traffic. And this avoids unintended congestion and it improves monitoring and troubleshooting. So with careful planning, including the correct uplink sizing, logical segmentation via VLANs and link aggregation, multi-switch NDI unicast networks can scale reliably, maintaining performance and stream integrity even in the most demanding environments. Until now, we've considered NDI operating within a single subnet, a flat layer 2 network where devices can discover each other automatically using MDNS and broadcast-based mechanisms. But as deployments scale, dividing networks into multiple subnets is common to improve manageability, performance, and security. However, by default, NDI discovery mechanisms like MDNS don't work across subnet boundaries. And this means that a source in one subnet is not automatically visible to receivers in another. Unless specified solutions are implemented, of course, we need some primary options for enabling NDI across subnet boundaries. First of all is NDI Discovery Server, which is recommended. It's the most robust and scalable method to deploy the NDI Discovery Server. This replaces MDNS with a unicast-based registration system, so all NDI devices, both senders and receivers, are configured to communicate with the discovery server itself. This allows devices across multiple subnets or even routed networks to discover each other reliably without relying on multicast. The second option is manual configuration via NDI Access Manager in scenarios where a discovery server is unavailable. NDI Access Manager allows you to specify the IP addresses or host names of NDI sources manually. This method bypasses automatic discovery but requires precise planning and static IP management. It's best suited for fixed installations with known devices. Third option is multicast routing, which is an advanced option. The network must support multicast routing through protocols such as PIN sparse mode if multicast streaming is used across subnets. And this allows NDI streams to reach receivers across routed segments, but does not solve discovery. Multicast routing is only part of the picture. It must be combined with manual configuration or a discovery server. So choosing the correct approach depends on your network topology and the scale of the deployment and whether multicast is being used for streaming. In all cases, reliable NDI operation across subnets requires thoughtful planning and coordination with network infrastructure. NDI and Dante are two of the most widely adopted AV over IP protocols, each optimized for different use cases. Understanding their core differences in terms of transport, discovery, synchronization, and network requirements, well, that's essential when designing reliable and scalable systems, especially in multi-subnet environments. Dante was explicitly developed for real-time audio. It uses unicast transport by default. A multicast is supported for specific use cases, but it must be explicitly enabled. Its low bitrate and deterministic behavior make it ideal for large-scale audio routing. NDI, designed for high-quality video transport, also uses unicast by default, with multicast available starting from NDI 3 for high-density distribution scenarios. Unicast provides flexibility but requires careful bandwidth planning in larger deployments. Discovery and subnet supported Dante devices rely on Dante controller for centralized management, whereas discovery and synchronization require all devices to reside in the same layer 2 domain, unless Dante Domain Manager or DDM is being used. That's a licensed paid solution which enables secure cross-subnet operation, device authentication, and advanced policy control. NDI, on the other hand, uses MDNS by default for local discovery within a subnet. And while MDNS is suitable for small, flat networks, it does have limitations such as poor scalability, reliance on multicast, and incompatibility with routed environments. For this reason, the NDI Discovery Server is the recommended solution for all but the simplest deployments. It replaces multicast-based discovery with a reliable unicast-based registration system that ensures consistent visibility of NDI sources across subnets and complex topologies. Alternatively, NDI Access Manager can define static source IPs manually, but this requires careful planning and is less scalable than a discovery server. When it comes to synchronization requirements, Dante relies heavily on PTP or Precision Time Protocol for clock synchronization across all devices. Now, accurate and consistent PTP distribution is critical for phase-accurate, low-latency audio transmission. Any disruption to PTP, such as jitter, loss, or asymmetric delay, well, that can compromise the entire audio network. NDI doesn't use any synchronization protocol such as PTP. Each stream is self-contained and synchronization is managed at the receiver level. So while this makes NDI more flexible and resilient to timing inconsistencies, it also means that precise inter-device synchronization is not guaranteed. An important note here is that in shared network environments, high bandwidth NDI traffic can interfere with Dante's PTP timing messages, especially if the two systems operate on the same VLAN or if network switches don't prioritize control of traffic correctly. For this reason, it's strongly recommended that Dante and NDI be isolated into separate VLANs or physical network segments to ensure the stability of both ecosystems. Now, when it comes to best practices in hybrid deployments, when deploying both Dante and NDI in the same facility, make sure to use separate VLANs or dedicated switches to avoid traffic interference. Make sure that multicast and PTP settings are carefully controlled for Dante, and avoid deploying NDI multicast on switches also carrying Dante traffic. Make sure to monitor network utilization and latency to preserve audio timing integrity. So by understanding and respecting the distinct requirements of NDI and Dante, particularly regarding synchronization and traffic isolation, you can build high-performance AV networks where both protocols coexist without any compromise. Although NDI is designed primarily for Layer 2 or local subnet environments, it can operate across Layer 3 networks as long as the proper discovery mechanisms are in place. By default, NDI uses MDNS, which relies on multicasting and is limited to a single broadcast domain. Now, this means that NDI sources and receivers on different subnets will not automatically discover each other, so the recommended approach is to use the NDI discovery server to enable reliable operation across routed networks at Layer 3. This replaces MDNS with a unicast-based discovery model, allowing devices to register and discover each other across subnets without requiring multicast routing. Unlike other AV over IP systems, NDI doesn't require additional clock synchronization or domain management services at Layer 3. However, administrators must ensure that the discovery server is reachable by all NDI devices over IP. Also make sure that routing between subnets is correctly configured, and firewall rules allow communication on the necessary NDI ports, because these measures enable NDI to scale effectively across complex Layer 3 infrastructures, providing flexibility without centralized licensing or time-sensitive protocols.